Welcome to part 4 on modeling. In this section, we're going to look at Newton's law of cooling. We know by observation that objects tend toward the temperature of their surroundings, also known as the ambient temperature. A formula may be derived by using this concept of tending toward ambient temperature over time. We can find the temperature of an object with respect to time using Newton's law of cooling. And this formula, although it might look a little intimidating, hopefully will make more sense once we go over all the variables and what they represent. The first one is capital T of lowercase t. This represents the temperature with respect to time. So capital T is the temperature and lowercase t is the time it takes to get to that temperature. And then capital T sub A is the ambient temperature. T sub 0 is the initial temperature when time equals 0. And K is the rate of temperature change. We usually have to find this to complete the question. And we'll have some examples to show that. And then lowercase t is time and could be in seconds or minutes or hours. And units will depend on the context. So I'm going to read you the formula for Newton's law of cooling. It is capital T of lowercase t, so T of t, equals T sub A plus the quantity T naught minus T sub A multiplied to E raised to the negative KT. The reason this is a negative K is because most of the time the object we are looking at is cooling. And if something is cooling, its temperature is decreasing. And if we look at the curve or graph the temperature with respect to time, we can say that it makes an exponential decay curve. But notice that if we look at it with respect to the formula has been shifted up T sub A because the object will tend toward the ambient temperature. The temperature of the object will approach a horizontal asymptote at the temperature of its surroundings, the ambient temperature. Let's take a look at our first example. An object is heated to 100 degrees Celsius. That would be boiling. And it's then allowed to cool in a room whose temperature is 30 degrees Celsius. So we know that the object is going to tend toward the temperature of the surroundings, so the ambient temperature. So we know that T sub A represents the ambient temperature, and it is 30 degrees Celsius. So we know we have a horizontal asymptote along y equals T sub A, the ambient temperature. And we also know that at time 0, the temperature of the object was 100 degrees, and it is going to approach this horizontal asymptote at 30 degrees Celsius. So we can now write an equation or a function to represent this situation. We know that the ambient temperature is 30 degrees, and we know that the initial temperature, T sub 0, T naught, is 100 degrees. If we subtract the ambient temperature, there is a difference between the two of 70 degrees. Then we multiply by E raised to the negative K times T. So this will equal 30 plus 70 E raised to the negative KT. This is the generic function for this situation. And then it says if the temperature of the object is 80 degrees Celsius after 5 minutes, find the temperature at time t. This is a critical piece of information because we know that 5 minutes in, the temperature was 80 degrees. We can now calculate the rate at which the object is cooling. So we will substitute T equals 5 and the object's temperature, T of 5 now, equals 80 degrees. T of 5 equals 80. And I'm going to substitute 5 in for time. I cannot find the temperature at time t until I find K. So I must find K first. I would say this is the hardest part of these problems, is recognizing that there's an intermediate step where you have to find K first. So I'm going to subtract 30 from both sides, and I'll have 50 equals 70 e raised to the negative k times 5. Then I'll divide both sides by 70. This gives me 5/7 equals e raised to the negative k times 5. Next, I will take the natural log of both sides to solve for k. The natural log of e is 1, and I can bring the exponent down. Now I have the natural log of 5/7 equals negative k times 5. So I will divide away the negative and the 5 on both sides, and this will give me just k. Now remember, it has to be a decrease, so I'm going to have to put that negative sign on there once I figure out what k equals. K should be positive, and then the negative will bring it into the decay region. Putting this in my calculator, the natural log of 5 divided by 7, all divided by negative 5, gives me 0.0672944. Now, this is pretty important to keep in your calculator, because if you don't, you will end up being off by a substantial amount by the end of your calculation. So you need to leave it at least 5 decimal places. If you don't, your temperature starts getting all messed up and you'll be off by a few degrees. So keep at least 4, but I would prefer 5 decimal places. So I will let k equal 0.06729. And if you want, you could even leave it in your calculator for the whole problem until the very end. Just store it in letter K or something like that. So if I want to find the temperature at time t, I can now write the whole generic equation, because I now have the rate at which the temperature is decreasing and tending toward the ambient temperature. T of t is equal to 30 plus 70 e raised to the negative 0.06729 times t. The last part of this video asks, when will its temperature be 50 degrees Celsius? Well, if we know the temperature, then we can say the temperature with respect to time is equal to 50, and therefore we have 50 equals 30 plus 70 e raised to the negative 0.06729 times t. And again, we need to find t before we can answer this question. We need to know, when will its temperature? So when will time allow your temperature to be 50 degrees? Subtract 30 from both sides, and that will give me 20 is equal to 70 e raised to the negative 0.06729 t. Divide both sides by 70. That will give me 2/7 is equal to e raised to the negative 0.06729 t. Take the natural log of both sides. The natural log of e is 1. Bring the exponent down front. That gives me the natural log of 2/7 is equal to negative 0.06729 times t. Divide both sides by negative 0.06729. And I have t is equal to this put in my calculator. So the natural log of 2 divided by 7 divided by negative 0.06729 equals 18.61737. So it will take 18.6 minutes for the object to cool to 50 degrees.